In this video, we are going to look at an example of trying to figure out which order to integrate in for a double integral based on what the region looks like. So this one's asking us to calculate the double integral over the region D of y dA, and D is that region that's drawn for you there. It's in the first quadrant. We've got three bounding curves here. We've got xy equals 1, that hyperbola. We've got the line y equals x, and we've got the line y equals 2. So here is that shaded region that we're interested in integrating over. Well, if I look at my integrand, I can integrate my integrand with respect to x or with respect to y pretty easily. So order of integration is not going to matter as far as the integrand goes here. So let's look at the region. I can either hold my x constant and integrate with respect to y first, or hold my y constant and integrate with respect to x first. Okay, so notice what's wrong with, well, not necessarily wrong, let's notice what's more difficult, I should say, with integrating with respect to y first versus x. So if I integrate with respect to y first, we hold x constant. So I'm looking at bounding curves for my y direction. Well, notice on this left-hand side of the region, my bounding curve is the hyperbola, and my for the lower bounding curve, and my upper bounding curve is the y equals 2. However, when I hit this point of intersection, my lower bounding curve changes from the hyperbola to the line y equals x. If I get a change in my bounding curve, that means I'm going to have to split my integral into two pieces. It means I'm going to have to do double the work because I got to do the double integral twice. I really would prefer not to do that if I can get away with not doing that. Notice that then if I integrate with respect to x first, holding y constant, notice that my left and right bounding curves stay the same all the way through the region. So it's much easier to integrate with respect to x first and then with respect to y versus the other way around because I can do it with one double integral. All right, so in terms of holding y constant, integrating with respect to x first, this is the curve x equals 1 over y. This is the curve x equals y. So my x's go between 1 over y, and then looking at the intersection, this is y equals 1, and this is y equals 2. So I can set up my double integral in this fashion. When we do that, antiderivative with respect to y, of y with respect to x is just yx. Plug in our endpoints, we get y squared minus 1. That antiderivative gives us a 1/3 y cubed minus y. And then plugging in our endpoints gives us a final answer of 4/3.